This Zoom session is being brought to you by the fractal set of itself. All right, today we're going to go through P4 and P5. P4 is about radicals and rational expressions. P5 is about simplifying algebraic expressions. We start with squares and square roots. Given a square, this four-sided figure, and has a side S, for some reason the side is also called a root. I don't know why. That's an ancient habit, whatever. Is side S, root S, and area A. The area equals S times S, called S squared. So that gives you A given S. Now, if you invert that, we can say that the side S is the square root of A, and that's denoted by this. It's kind of like a fancy letter R enclosing the letter A. Not the best of notations, in my opinion, because it's sort of a little ambiguous. How much of the thing to the right of it does it contain? When you use it in practice, I recommend using parentheses just to make it unambiguous. Anyhow, so square root of A, or root A, is the solution, the positive solution to root A squared equals A. This is called a root or radical. Radical meaning having to do with roots. So a radical is someone who goes down to the root of things, you say. Now, okay, there's going to be two solutions to x squared equals A. For example, 2 squared equals 4 and -2 quantity squared equals 4. So there'll really be x squared equals A for x equals root A and minus root A. We'll be seeing more about that later. So for example, given S being 0, 1, 2, or 3, A is 0, 1, 4, or 9. Now, if you run that backwards, if A is 0, S has to be 0. If A is 1, S has to be 1. If A is 4, S has to be 2. But if A is 2, well, S is something called the square root of 2. If A is 3, S is the square root of 3. And a square root of 2, I can't give you the exact value in terms of a ratio of integers. It's approximately 1.414213562, which is accurate to 9 decimal places, 1 part in a billion, which is pretty good, but it's not exact and perfect. That's the problem. And unfortunately, basically, most numbers, when you take their square roots, you do not get a ratio of integers. These are what are called irrational quantities. I could tell you more about that, about how the Pythagoreans, when they figured out that the square root of 2 is not a ratio of integers, they freaked out. But that's for later. Yes, if A is a square of a rational number, P squared over Q squared, when P and Q are whole numbers, then root A equals P over Q. If it is not the square of a ratio of integers, then it is not a ratio of integers. And A is not, then square root of A is not. So, and if A is less than 0, then square root of A is not on the real number line. The reason why is that if you take a positive number and square it, you get a positive number. If you take a negative number, you get a square it, you get a positive number. Take 0 and square it, you get 0. And in none of these cases, you get a square which is negative. So the square root of -1 is neither positive, 0, or negative. It's a different kind of number called a complex number. And we will be seeing more about that somewhat later. All right, we proceed. In general, the square root of x squared is the absolute value of x. Positive, rather than since it's the absolute value, it has to be positive. If you graph y equals square root of x, it has this shape which looks like a parabola on its side. It starts vertical, moving vertically, and then it slows down, but never stops, and it grows like that. Similarly to square roots, there are cube roots. Cube root of x is a solution to a number which cubed is x. Cube of x cubed is x. So, and it turns out we don't have this ambiguity or we have with square roots. For any real number, its cube root cubed is x, and the cube root of the cube is x. And the cube root, its graph looks like this S-shaped curve. It's defined for negative numbers, and in fact, the cube root of negative x is negative the cube root of x. This graph is symmetrical around the origin. And we can go on to talk about nth roots. The nth root of x is the solution to nth root of x to the n equals x. If n is odd, then the nth root of x to the nth is x. If n is even, then the nth root of x to the nth is the absolute value of x. Even powers have this problem. A little bit gnarlier. Now we can talk about square root of x. We can call it x to the 1/2. And a cube root we can call x to the 1/3, and nth root we can call x to the 1n. And it makes sense. So for example, x to the 2 halves, which is just x, is x to the half squared, which is root x squared, which is x, so they cancel. X to the 3/3, you get a cube root and a cube, which cancels. X to the 4/4, cube, fourth root and fourth cancels, as it should. So we can define these x to a reciprocal power as roots of x. And we can define a ratio power, x to the m over n, as the mth power of the nth root of x, or equivalently, the nth root of x to the m. So for example, 64 to the 1/2. Well, a half is a 1/2 is a square root. 64 is 8 squared. 2 times a half is 1, and 8 to the 1 is 8. 64 to the 1/3. Well, 64 is 4 cubed, and a cube root of a cube cancels, and you get back 6. You get back 4. 64 to the 2/3 is a square of the cube root of 64. Well, okay, the cube root of 64 is just 4. So 64 to the 2/3 is 4 to the second, which is 16. 64 to the 3/2 is the cube of the square root of 64. And the square root of 64 is 8. So this is 8 cubed, which is 512. Now, the rules there I mentioned earlier, the rules for exponents, that an exponent to a sum is a power of a product of exponentials is a to the sum. A ratio is a to the difference. A product to a power is a product of powers. A power of power is a to the product of powers. And a to the negative x is 1 over a to the x. All these worked for whole number x and y, and they also work for fractional x and y. So these rules apply more generally. That often happens in math. You find a rule which applies for a certain kind of set of numbers, then you see if you can extend it to a larger set of numbers. Okay, so for some examples. Now let me say again that these odd numbers were keyed to a previous edition of the textbook. So these odd numbers are a little bit obsolete, and maybe I should erase them in future Canvas notes. We proceed. What is root 7 times root 28? What is root 38 over root 3? What is 4th root of 24 times 4th root of 54? Well, now we use the rule that, we use this rule, that a product of powers is a to the sum. Or, excuse me, what am I saying? That a product of powers is a power of the product. So here you have a half power of 7 times a half root of 28. So it'll be a half root, half power, in other words, the square root of 7 times 28. That'll be root 196, and this turns out to be 14. Exactly. Root 48 over root 3, we can put that root of a ratio. A ratio of roots is a root of ratios. 48 over 3 is 16, and so you get root 16, and that's 4. Here you have a product of roots, so that'll be a root of a product. 4th root of 24 times 54, which is 4th root of 1296. And your calculator can and does, well, this one has nth roots. Just have to know where to look on the screen. Excuse me. And that'll be 6. Here, we have a 5th root of a to the 6 times b to the 7. I have to simplify that. So it's a 1/5 power of a to the 6 times b to the 7. Because powers distribute over products, it'd be a to the 6/5 times a to the 7 times b to the 7/5. Now 6/5 is 1 and 1/5. 7/5 is 1 and 2/5. So this breaks into a to the 1st times a to the 1/5. This breaks into b to the 1st times b to the 2/5. Just a second, let me make a change here. Okay, and so this will be a times b times the 5th root of a times the 5th root of b squared. ab 5th root of ab squared. Root 32 plus root 18. Well, okay, the trick here with these is you want to remove a square factor of 32, the largest possible square factor. 32 is 16 times 2, and 16 is a square. 18 is 9 times 2, and 9 is a square. Root 16 is 4. Root 9 is 3. 4 root 2 plus 3 root 2. These are like terms. Add 4 and 3 to get 7. And so this becomes 7 root 2. Here they ask for 32 to the 2/5. Well, 32 is 2 to the 5th. That to the 2/5 power means you multiply 5 times 2/5, which is 2. You get 2 to the 2nd, or 4. 49, 4 nines to the minus half. Well, 4 nines is 2/3 to the 2nd power. You multiply these powers and you get 2/3 to the 2 times a half, which is 2/3 to the -1. And a negative power is a reciprocal, therefore 3/2. 1681 to the 3/4. Well, again, 16 over 81, that's a power of 2/5, namely a 4th power. So 2/3 to the 4th power, that to the 3/4 power. This is a repeated root, repeated powers, so we multiply the powers. 4 times 3/4 makes 3. So 2/3 to the 3. And okay, 2 cubed over 3 cubed is 8 over 27. Here we have what's called rationalizing the denominators. The problem being is that square roots, irrational square roots, are a pain in general, and dividing about them is an even worse pain. But there's ways to get them out of the denominator. Here's the trick. 1 over root 6, we take that and we multiply that by root 6 divided by root 6. This is just 1, and that won't change it at all. 1 times root 6 is root 6. Root 6 times root 6 is 6, so you get root 6 over 6. So now we have a rational denominator, therefore rationalizing the denominator. 3 over root 2. We have this pesky root 2 in the denominator. We can get rid of it by multiplying the whole thing by root 2 over root 2, which again just equals 1. And in the numerator, I get 3 root 2, and root 2 times root 2 is 2. So 3 root 2 divided by 2. 9 over root 3. Okay, pesky root 3 in the denominator. We get it out of there by multiplying the whole thing by root 3 over root 3, which is another version of 1. 9 times root 3 in the numerator. Root 3 times root 3 is 3. Now we can cancel 9 over 3 and get 3. So the end result is 3 root 3. Now you have more rationalization of the denominator. 1 over the cube root of x, which is 1 over x to the 1/3. Again, a pesky pesky root in the denominator. We get rid of it by multiplying by x to the 2/3 over x to the 2/3. Again, an alias for 1. 1 times x to the 2/3 is x to the 2/3. X to the 1/3 times x to the 2/3 is x to the 1 plus 2/3, which is 1, x to the 1. And then, okay, so this is a cube root of x squared, all that divided by x. 1 over 6th root of x to the 5th, that's 1 over x to the 5/6. And to rationalize that, we multiply it by above and below by x to the 1/6. Numerator is x to the 1/6. X to the 5/6 times x to the 1/6. Well, we add the powers. 5/6 plus 1/6 is 1. And so 6th root of x divided by x. And we have x 1 over 7th root of x cubed. That's 1 over x to the 3/7. Now to rationalize that denominator, multiply above and below by x to the 4/7. 4/7 because 3/7 plus 4/7 makes 1. So we'll get in the numerator x to the 4/7, in the denominator x to the 1st. So this will become 7th root of x to the 4th, all divided by x. Oh, one thing, yes, please. A piece of advice. You'll notice I made these division signs extra long. I strongly recommend that when you write things down like that, you make sure that the division signs are longer than the root sign, because if you write it as shorter than the root sign, then it becomes ambiguous. If you wrote this divide sign this short, then it would be, is it the 7th root of x to the 4th, all that divided by x? Or would it be the 7th root of x to the 4th over x? Slightly different things, completely different results. It would become ambiguous. And please, 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 let me warn you, in mathematics, ambiguity is not your friend. Ambiguity is your friend in poetry, in literature. Ambiguity is your friend in love and war. But that's because, unlike love and war and poetry and literature, mathematics has standards. Okay, that's it for this. Stop for this now.